Well, hey everybody, welcome to today's presentation where we talk about optional method calculations for a single family dwelling. Now, I did a webinar earlier and I got to apologize. As I did through the webinar and shifting all these screens on my software, I have nobody else monitoring and helping. So I realized that I was talking about something that you couldn't even see on the screen because the code book was up and I was doing some calculations in the background. So as a penalty to me, I am going to redo the video. And I'm not going to redo the webinar, but I'm going to redo the video. So again, accidents happen and I apologize. And again, I'm only human and I make those mistakes. So I'm going to do the whole presentation again and maybe I can get it done in less than an hour. We'll see. But I'll tell you up front, today's presentation is going to be on the optional method, doing the calculations for a single family dwelling. We have already done a presentation on the when doing the standard method, and we already have that. That's available on our YouTube channel, and that goes into all of the things that you need to know to do the standard method, which is part 3 of Article 220. But it also talks about sizing the neutral conductor. The reason that's important is because when you're doing the optional method, you don't use the neutral calculations using optional. You have to use the standard method. So well, we're going to talk about the optional method today to get our ungrounded conductors, our HOTs, if you will. You're not going to utilize the optional method in order to size a neutral. You're going to have to go use the standard method to do that. Okay, so go watch that in the standard method. And again, it's going to apply here. You just do the optional method and do the standard method to determine what the neutral is. Okay. All right, so let's get into it. Again, I apologize to those that attended the webinar. My bad. All right. Hopefully you heard me talk about it, but you didn't see it. And that's the problem. All right, so let's go to the calculation. All right, so here we go. Again, water heaters, clothes dryers, counter-mounted cooking units, wall-mounted ovens, all of that electric heat is all going to be based, when it shows kW here, it's really going to be equivalent to kilovolt amperes or kVA. So if you see kW here, kilowatts, it's really kVA because we need it to be converted into VA ultimately. So just keep that in mind. When you see anything that says kW, we're going to have to convert that into VA. All right. So 35 feet times 55 feet, that is the dwelling units outside dimensions. That's what it says that we have to deal with in the code. So we'll see that when we look at the code book here in a second. We're just going to cover the things that are here first. We have a front porch that is actually the 7 by 10. That square feet is actually covered in the outside dimensions of the dwelling, so we're going to have to take that back out because the front porch is an open porch and it's not included, and the code tells us it's not to be included. That says the same thing in the standard method, says exactly the same thing here in the optional method. Okay. We have small appliance branch circuits. The code requires a minimum of 2, and that is in the requirements in 210.11c1. And in this case, we have 4 that we're dealing with. So we've got 4 of them that we've got to take into account for this optional method. And remember, in the standard one, we had the same concept. We had to do 4. The next is the laundry branch circuit. And here you see we have 2 of them. But in accordance with 210.11c2, we're going to have at least 1. And this is a single family dwelling, so we're going to count for 1. But in our calculation, there's 2 of them. So we're going to count. We have to count for both. Okay, because we've got 2. We got to count for them. You can't just get rid of one of them. The next you see in our list, as we're just kind of moving down the list here, is the dishwasher. The dishwasher is, the water heater. I guess I should have done the water heater. So where's my hand here? Right. Oh, can't go up there. Won't allow me to do it. So I'll do my mouse. We're right here. Water heater. 4.5 kW. Okay, so again, kW, we need it in VA. So 4.5 times 1,000, or you can just try to look at it and see the K. You'll learn that 4.5 is 1,000. So it's 4,500 watts, which is synonymous with VA, and we need VA. We're going to do calculations in VA. The next you'll see is the dishwasher. Now, this dishwasher is 10 amperes. It's 120 volts. So in order to calculate it out and find the VA, we go the amps times the volts is going to give us what we need. So 10 amps times 120 volts is going to give us our VA, and we need that later, and we'll do that later. In-sink waste disposer, okay, your garbage disposer. This one is a half horsepower motor. It's 115 volts. Well, this is the only motor in here, or the only thing that gives us a horsepower. Everything else gives us the amps. So what we have to do with this half horsepower is we're going to have to go to 430.248, and that deals with single phase motors. And then we'll look down the list and we'll find the column with the 115 volts, and then we're going to find the half horsepower motor, and that's going to tell us what the FLC is, and that's what the amps we're going to use. And we're going to take that amps, and then we're going to multiply that by the 115 volts, and that's going to give us our VA. We're going to do that later. Don't worry about it. All right, the next thing we're dealing with is a trash compactor. Don't really see those much anymore, but 7.5 amperes at 120 volts. So we do 7.5 amps times 120, and that's going to give us our VA for that. We'll do that later. I've got 3 attic fans, 4.2 amps each. It's 12.6 amperes at 120 volts. Again, 12.6 amps times 120. That's going to give us our VA. I guess you could go 4.2 times 120 and then do it for each one and then add them up again, but why would you? Why waste the time? Clothes dryer, we have a nameplate of 5.5 kW. Again, kW, we know that it's 5,500 VA. That's what we're trying to ultimately get to at 240 volts. We have a counter-mounted cooking unit, 7 kW, 7,000 VA, and that's at 240. We have a wall-mounted oven at 6,000 VA or 6 kW. We can again convert that to VA, and that's 240 volt load. We have electric heat. Okay, 3 banks of 5 kW heat. Okay, and I will tell you up front, this air handler is, no matter how you design it, this air handler does utilize an application where, in many cases, if it was a heat pump, then the air handler would also be associated with what we call supplemental heat. But because this doesn't say supplemental heat, we're taking this as electric heat. Okay, but in our case today, because of what's presented, we're going to take that air handler and we're going to add it to the electric heat as if it's in a system that's also going to blow that heat out. Okay? All right? So just keep that in mind up front. I'm telling you that up front, so it's not to avoid any confusion. The next thing that we have, again, is the air handler unit, which is 3.2 amperes at 115 volts. So I'm going to take that 3.2 amperes times 115, and boom, boom, boom. There you go. You're going to get your VA. We have air conditioning compressor, 16.6 amperes, 230 volts. We're going to have to do the math again. 16.6 times 230 is going to give us the VA. We're going to need that later. Now, you could do that all up front, write it to the side. That way you don't have to do it later. Save you some steps if you want. But again, we'll get to them systematically as we move through this. The next is a condenser fan motor. It's 2 amperes. It's 115 volts. Again, 2 amps times 115. It's going to give us our VA. Again, we need VA to work all this. So we kind of got the lay of the land. We know what we're working with. We kind of set the tone on where we're going here. And what we're trying to do is determine, based on these loads that we're given in this dwelling unit. And incidentally, when it comes to these calculations, single family dwelling and dwelling unit are synonymous. They mean the same thing. You could have an individual dwelling unit that goes to, let's say, an apartment. Okay, but a dwelling unit, as defined by the National Electrical Code, has 4 elements in it: cooking, sanitation, living, and sleeping. A single family dwelling has all those things. An individual dwelling unit has all those things. They're both a dwelling unit. Okay, the reason we define 2 different ones is because there's certain applications of the code where we need to define what a single family dwelling is to see whether something applies. But in general terms, the dwelling unit is something that encompasses all of those elements into that package of a dwelling unit. So I don't want people to get lost in that. A dwelling unit, when it talk about single family dwelling, are one and the same when we're doing these calculations. Okay, don't forget that. All right, so let's kind of go back to the presentation and make sure that we're covering. Actually, what we want to do is we want to go now to the NEC. And the reason we're going to go to the NEC is because we want to set the foundation. What does it take to say that we can use the optional method? That's important because we have to know if we can even use part 4, whether or not we're stuck in part 3, which is a standard method. So we're going to go to the NEC. Now, when we look at the NEC, we're going to see that you have optional method right here. And it is part 4 right here. Now, we've covered the standard method in part 3 before in another video, so go watch that. In fact, you really need to know how to do the standard method before you do the optional method. Because like I said before, when you do this optional method and you finally get all this worked out and everything, then you're going to try to size that neutral. Sadly, you're going to have to go over and use the standard method to size that neutral at that point. So, I wouldn't start with the optional, because once you get to it, you're kind of left hanging. Now you're going to have to do the standard just to find out what that neutral. Now, between me and you, since most of these dwellings, I say, are going to fall between 100 and 400 amperes, then usually you can buy an off-the-shelf SCU or an SCR, and you're pretty much going to get covered when it comes to the neutral. Okay? But you still need to know how to do the neutral calculation. And we covered that in the standard method. We're probably not going to cover it in this video for keeping it short and concise. But I want you to know that you can't use the optional method to size the neutral. Okay, now, what tells me in the code that I can use the standard method? All right, so here in the code, you're going to see that when we're dealing with the dwelling unit. Now, again, many people get lost in that word, in that terminology, and they think dwelling unit only means an apartment. Please don't go there. It's not what it means. Every educator in the country who does a book, who does a video, who does educational seminars, who does other videos, are going to show you that the optional method is to be utilized here. You don't need to be clever and think anything other than that. It is what it is, okay? It's a dwelling unit. Now, the reason we know that, be honest with you, is because when I come up in here and I start looking at the dimensions and everything, why would I need to deal with if it was only a dwelling unit and it didn't apply to a single family dwelling if it's telling me that garages don't get considered? Most of those apartments don't have garages in the calculation, okay? Usually the common area would have a garage, but not the apartment complex. It makes no sense. So why would it make sense? I think my first explanation of it makes perfect sense. Though you're going to use this. So it says dwelling unit, but be honest with you, single family dwelling meets all those elements to be a dwelling unit. There may be other aspects in the code where we call it a single family dwelling, and that's important, okay? Especially if we have a two-family dwelling where we have a separation by a firewall, and then we have two separate single family dwellings. But each one of them constitutes a dwelling unit, okay? Don't get lost in that. All right, so let's look at it here. And you can agree to disagree. Perfectly fine. Now, it says, this section applies to dwelling unit having the total connected load served by a single 120 240 volt or 208Y120 set of 3-wire service or feeder conductors with an ampacity of 100 or greater. So we're kind of meeting some caveats here. When can I use the optional method? Well, it's got to be 120 208 or a 208 120, and it's going to be a set of 3-wire, so it's going to be single phase. Now, if it was a 208 120 3-phase, then you would have A, B, and a C, okay? But then it wouldn't be a 3-wire service, okay? It would have 3 phases and a neutral conductor. Well, in this case right here, when I'm applying it, I've got 2 phases and a neutral conductor, okay? And then I might have an equipment grounding conductor, which generally isn't thought of as being part of the circuit conductor. So it still would be a 3-wire application. All right, so in our case, 120 240 volt, and that's what we're using today. That's what ours are going to be on. But it would also apply to a 208Y120. And in that building, you might have a 3-phase 208Y120 where you have A, B, and C phases to ground, which is 120 volt loads. Or you might have A and B phase with a 2-pole breaker. That's a 208 single phase. Okay, and that is A, B, or C. Okay, again, we're dealing with a Y system. And then, of course, if you have a 3-pole breaker that's going on it, then that would be a 3-phase 208. Okay, not what we're talking about here. We're talking about 120 240 volt or 208Y120 applications, and we're talking a 3-wire service or feeder. Pretty much going to lock us into the single phase application. You with me? Okay, we're on the same page. Now, let's keep on, because nothing so far has told me that I can use part 4 yet. Now, it says, it shall be permissible to calculate the feeder and service load in accordance with this section. What section? This section, 220.82, instead of the method specified in Part 3 of this article. So everything that's in Part 3, forget it. We're locked into Part 4. We're going to do it here. All right? Now, as long as 100 amperes or greater, we're locked in. As long as it's 122 40 volt or 208 Y120 3-wire service or feeder, we're in. We're all good. We're all in. Now, how do we do this? How do we use 220.82? Where there's an A and a B and a C. We're going to focus on B and C, but A gives us those parameters that we got to follow. So in this case, we're going to say that we're over 100 amps. Okay, so we're good to go. And we're dealing with the 12240 208 Y120. We're good to go. Now, we're getting away from Part 3. We're in Part 4. It says the calculated load, that's the ultimate load after you do all the calculations, shall be the result of adding the loads from 220.82B and C. Two separate ones, and we add them together. All right? And then lastly here, it only serves to remind you what I've been saying all along, that when you're doing the feeder or service calculation, remember that when you're sizing the neutral, you have to use a standard method and meet all the rules in 220.61. Okay? So just remember that. That does fall under the standard method. So it falls under Part 3. So you're governed under Part 3. And follow all those rules associated with that. All right? So when you're doing the neutral, Part 3. Just saying. Keep that in your mind. Now, you have a B and a C. B is the general load, and we're going to talk about all those general loads today. And of course, then you've got C, which is heating and air conditioning, and you have 6 selections here. And you're going to take the largest of the 6 selections. Okay? That's what we're going to do today. Okay? All right. So let's move back to our calculation and or back to what we've got going on in the presentation. Now, several things I told you up front. Even though this heat right here is going to be considered separate, and it is not more than 4, it is 3, we are going to add the blower in it because the way this one's designed, and I'm telling you this up front, and on your exam it'll tell you that as well, we're going to consider the air handler in because it also is going to be utilized to blow that heat. If I was using fixed space heating like baseboard heating, then it typically wouldn't have the blower motor associated with it. Okay, in our question, we are going to associate the blower because it's used to blow the cooling, but in our case, the way this heat is set up, it is also utilized and they're separately controlled, but it also figured in blowing that heat as well. So I'm just telling you that up front. If your exam has separately controlled baseboard heating, then it wouldn't have to add the air handler in that. Okay, just making that clear up front so there's no confusion. All right, so we've considered all this. So let's kind of get started. All right, first things first, you remember what it said about the 3 VA per square foot? In the standard method, it's kind of convoluted, right? You got to go to 220.12, and then that tells you to go to the occupancy type. And then you go to the occupancy type, and it says for dwelling unit, it's 3 VA per square foot for dwelling unit. Bear with me here for a second while I put this on pause, because otherwise I'm going to get a bunch of beeps during this presentation. Okay, so we don't have to do that here. Because in the optional method, it tells us right up front what it is. And I'm going to let you see that. Right up front, it tells you. It says right here, it says 3 VA for general lighting and general use receptacles. Remember back in the standard method, it talks about general lighting, and it didn't say anything about general use receptacles unless you saw the little asterisks. And once you saw the asterisk, you went to the bottom, 220.14, and it said, oh, go over to 220.14. The general use receptacles, well, the values of those already get encompassed in that 3 VA per square foot. A lot of people confuse that 180 VA per strap. That's for commercial applications. Has nothing to do with dwelling units. Don't get lost in that. Here, all we're saying is, you know those general use receptacles? Even that bathroom receptacle, that's general use. That's already encompassed in the 3 VA. You ain't got to do nothing else. Well, before we had to kind of work our way through that. Here we don't have to. It says it right here on the screen. Black and white. Now, as far as the floor area, nothing changed from the standard method. You're going to use the outside dimensions. If you have multiple floors, you're going to use the outside dimensions for each floor. If you have open porches, garages, or unused or unfinished spaces that aren't adaptable for future use, for example, an unfinished basement is still adaptable for future use, and you're going to have to count that square footage. But an attic that is not designed to go up there and handle storage, in other words, it's just rafters, it's not really adaptable for future use. You're not going to walk up there. But if I have an unfinished attic that has adequate floor joists and a flooring down, and it's still considered attic, but I could finish it off, then it is adaptable for future use, and I'm going to have to count that square footage area. Okay? Just kind of subtle things to keep in mind. Now, you noticed also in the standard method when it talked about the small appliance branch circuit that was 150 VA, and you had to end up working your way through the code to get to that. Well, here it's already right there, plain as day. It says 1500 VA per small appliance branch circuit. So that's what we got here. And in our calculation, we had 4 of them. So we got to take that into consideration. Now, what about the laundry? We have 2 laundry circuits in our calculation. And they also are at 1500 VA. It says it all right here in the optional method. Makes it really, 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 really simple. Now, one of the things that were different previously is that when we went through all of this, we also then applied demand factors. And that's where we went to 220.42 and we had the first 3,000 at 100, you remember, standard method. And then the next 117,000 at 35%. And then the remainder over that is at 25%. You don't have that here. We've got a first 10,000 at 100 and the remainder of our calculation here under B at 40%. Now this only applies to B, doesn't apply to C. This only applies to B. Okay, so we're going to get a pretty healthy demand factor here. You just don't have to do it to those first 3 items, the general use or general lighting and general use receptacle and the appliance and laundry. You don't apply it to that right away. You just keep on adding these things up. That's what the optional method is all about. But there's a caveat. You're going to have to take the nameplate value of all your appliances, the nameplate value of your ranges, wall-mounted ovens, counter-mounted cooking units, clothes dryers, and water heater, and any other motor that you might have that is permanently connected motor that is not covered in the appliance application that we're going to talk about in a second. Okay, so I could have other motors. Like, for example, if I have a pool house and that load is there during my calculation, it didn't come after, but it's there, and I have that as an appliance and it's a motor, then I'm going to have to consider it. If it's a motor pool pump motor, it's not considered an appliance, then it might be covered as a permanently connected motor, and then I'm going to have to calculate that kVA into my calculation. Okay, why not? It's there. It's a load. Why wouldn't I consider it? Okay. So, a lot of people go, no, you don't know, but they're wrong. I can guarantee you they're wrong. All right, so let's kind of go back to what we're looking at. So, that's what we're seeing here in the code. So, let's go back to the presentation and kind of move through this because we got to move. All right, so here was our outside dimensions. And again, focus more on me and what I'm talking about in the graphics than the text because I know that I probably left something legacy from the standard method that we don't want to get caught up in that. I just want you to listen to me and follow along. And hopefully, which I didn't do during the webinar, was make sure that I was on the right screen. But I'm going to really focus on that here in this replay. All right, so it was 35 times 55. And that would be 1,925 square feet. And of course, you remember it says included in this dimension here, so we got to take it back out because remember it says right here, open porches, garages, whatever. It's not, so we got to take it out. So in order to find out what we take out, we go 10 times 7 or 7 times 10, whatever your flavor, and that's 70 square feet. So of the 1,925, I'm going to take 70 away, and that is 1,855 square feet. So 1,855. Now, remember what we said? It's 3 VA per square foot. We didn't have to go to what? 220.12 and look it up for the occupancy type. We're dealing with the one family dwelling. We're able to use this optional method. We go straight. It says 3 VA like we read it earlier in 220.82B. And so that is 5,565 VA. Okay, write that down. All right, so the next we kind of check these off. We're going to deal with the small appliance and laundry because, again, we get to deal both of those together when we're dealing with the optional method. So here's a small appliance. There's 4 of them. Remember what we said earlier? It's 1,500 VA each. So here, 4 times 1,500 VA is 6,000. Remember, that is what it says right here in the code book. Right here. 1,500 VA for each small appliance branch circuit. And again, it also says that for the laundry. So when we get to the laundry, no need to come back to the code because we kind of know what we're talking about here. So we've got that, and we're going to write that down. So that's 6,000. That's our small appliance branch circuit load. Next, the laundries. We had 2 of them. Remember what we just read? 1500 VA per. That is different than the standard when it comes to the fact that we had to get there by going to a specific section. Here, it's all right there. We already read it. And that's the only reason it differs. It's still 1500 VA. So there's two of them. So it's 2 times 1500. That's 3000 VA. So we write that down. Now, we had 5,563. We had the 6,000 for the small appliance. And we had the 3,000 for the laundry. Okay? Now, again, how does this differ from the standard method? At this point, we would apply a demand factor. Again, first 3,000 at 100, the next 117,000 at 35%, and then the remaining over that would be at 25. We don't do that here. We just write this number down, and we continue on and move into the appliances now. Okay, that's the big difference. The other thing to remember that if we have an optional method and our calculation comes up to be less than 100, guess what? We can't use the optional. We have to go use the standard because the optional is limited to 100 amps or greater. Just remember that. Don't want to get you messed up in dealing with that. All right, so we added these all up, and that came to 14,565 VA. There you go. So that we write that down, we set that aside. That's our total value. We just added all three of those up. Now let's move on. So what are we dealing with next? We're dealing with appliances, the water heater, dishwasher, in-sink disposal, trash compactor, and the attic fans. We're going to deal with those. All right. Now, ironically enough, the water heater is an appliance, but if we look at the NEC, you're going to see that under these options here, you'll see that water heater is by itself under D, and we're including it kind of as an appliance. But just so you understand, the water heater is also included in there, and you're taking the actual nameplate that you're going to get from that, okay? Still might have to do some math, but you're getting that math from the nameplate, okay? I just wanted to make it clear as we move through with this. So in the presentation here, I've got a 4,500 VA, and I got all these things. So let's work on these now. So first things first, though, what's an appliance? It designates that utilization equipment commonly built in standardized types and sizes and installed as a unit to perform a specific function. So we have a definition in 100. Now, in that definition in 100 for appliances, which is governed by Code Making Panel 17, which I sit on, which is dealing with 422, we give a bunch of different appliances in there, okay? But what's really important to understand, and of course up in 680 when we're talking about, let's say, a unit heater for a pool, we start making references to that as an appliance as well, okay? It's a unit heater, but we talk about it as an appliance. So that's important. But when you look at appliances, it makes reference to the term utilization equipment. And utilization equipment right here is also defined in the National Electrical Code. And so when you go look at utilization equipment, it gives you a real unique definition. So the reason I want to show you that, because I had people that question what an appliance is and how we'd apply it to these optional methods. So we're going to go to the code book real quickly, and hopefully quickly, and that I can go down here and go to 100 and show you what we're dealing with appliance. What is an appliance? It is utilization equipment. Generally, other than industrial, okay, we're a single family dwelling, so it's not industrial unit equipment. It says that is normally built in standard size of types and is installed and connected as a unit to perform one or more functions such as a clothes dryer, air conditioning, food mixer, deep fryer, and so forth. But it's utilization equipment, all right? So when you see the terms such as, that's not all inclusive, okay? There's stuff that perform utilization equipment that, and we have a definition of utilization equipment that can constitute a exactly on what an actual appliance may be, the function, okay? So when I go to utilization equipment, and I do want to go to that just so you can see it while we're just kind of, oops, right out of definitions there. Is like I just blinked and it was gone. Right here, utilization equipment. So utilization equipment, it says equipment that utilize electric energy for electronic, electromechanical, chemical, heating, lighting, or similar purpose. Okay? is going to be considered utilization equipment. And so when we go back and look at the term appliance, only then can we appreciate the fact that when it says appliance, that it says utilization equipment, generally other than industrial, that normally built in a standard size or type and is installed or connected as a unit to perform one or more functions. Okay? One or more functions. Okay? Clothes washer, it has a motor that spins it and it washes clothes. Air conditioning unit, it's one function and it's an appliance, but they make them in standardized types or sizes. Okay? And so I don't want you to get lost in that and make sure that people lead you astray when it comes to what an appliance is and an understanding of how you apply these things. Okay? All right. So let's get back to the presentation so we can kind of move on here. The one thing that's also different that I want to make you aware of is that under the standard method, we get to apply, when you got 4 or more appliances, we get to apply 75% demand factor. We don't do that here because we're so gracious with the optional method where the first 10,000 at 100 and the remainder at 40 that we don't get to, we're just going to take the appliances at their nameplate value. So it's a give and take. So we don't get to apply the 75% demand factor. That is a standard method calculation thing. It's not something we're going to do with the optional method. So I want to make sure that you don't lose sight of that. All right, so that's just kind of one of the differences to move on. Now, let's look at all. So here we're dealing with them again. The water heater kind of is covered also alone, but we're going to lump it here and kind of do it the same because it just adds all of these appliances and the water heater together. I will remind you that under 422, we do refer to a water heater as appliance. Okay, but again, in the optional method, they call out water heater by itself. It's a moot point, still covered here, so we'll go over it. So the water heater is 4,500. Okay, we show you here how to convert that. So we need that in VA, so it's 4,500 VA. I think we all get that. The dishwasher, now we got to do the math. So it's 10 amps times 120 volts. That is 1,200 VA. We have the in-sink waste disposal. Well, we had that half horsepower. So now we're going to have to get the actual amps here. This is the only one in this equation that does it this way, or this question, I guess. Only one that's done this way. So we got to go 430.248. So I'm going to do that here. I did not do that in the webinar, so that's good news. You're going to get a little more here than you did there. So I'm going to go to 430, and I'm going to go to, and when I'm doing the electronic version, I like to go to 440 and go backwards. It just makes it easier. All right, so 248 because it is single phase and is alternating current, and it was 15 amperes, and it was, 115 volts, excuse me, and it was a half horsepower. So this is where you get the 9.8 amperes, and that's what we're going to use. Now, once we know the amps, then we can multiply and find out what the VA is. Okay. So with that said, we're going to come back to me, and we're going to look at. So we did that, and that was 9.8 times 115 volts. Use what's in the equation, and that's going to be 1,127 VA. The next is a trash compactor. That's 7.5 amps. Again, multiplication. 7.5 amps times 120, because that's what's given in the question. So that's 900 VA. We write that down. And we had 3 attic fans, as you see here. 4.5 amps each times 3 is 12.6, saving us time. We just do 12.6 amps times 120, because they're all 120 volt attic fans. And that is 1,512 VA. We're adding all these up. We have 9,239. That is what all our fixed appliances are. Plus, we've also thrown in the water heater as well. But we're not done, because if you go look at the code, and we'll do that, if you go look at the code, you're going to see, and we got to go all the way back to 220 now to get there, is what you're going to see now is that we're at this next step. That was A. We did A. In fact, we did A and we actually did D because we added the water heater with those appliances there. Now we're going to do ranges, wall-mounted ovens, counter-mounted cooking units. And the good news about the optional method, folks, is we don't got to worry about 220.55. We don't for this application. All right? Whew. So here we're going to go back to the calculation, and we're simply going to take the actual nameplate values of it. So before we do the ranges, we're going to do the dryer. So the dryer was 5.5. And again, the beautiful thing about this is we don't have to use the values in 220.54 either for dryers. We could take the nameplate is what we take. All right. So, and I apologize. I was talking about ranges and then I jumped to here, but you'll get it. No problem. So 5.5 kW, we know that that's going to be 5,500 VA. And so when we do this, we're taking the value that we had from over here, which is 9,239. We wrote that down. That was our appliances. Now we're going to move through the dryer and move through the air conditioning. The cooking and the clothes dryer. So we carry this over just to keep it there to remember it for later, but we'll add it all later and not worry about it. So 5,500 VA. So now it's 9,239. This is what we had previously up here. And 5,500 VA. Ignore this right here. This is a legacy. It was a mistake. I didn't carry it over. I apologize. So it's 9,239. Again, this was your appliances. And now we're adding, because we're still under B, we're adding the 5,500 VA. So that gives us 14,739. Now we're going to carry that over, put that here on the side. And we're going to look at the counter-mounted cooking and the wall-mounted oven. Remember, if we go back and look at the code now, it says right there that we're going to take it at the nameplate value. And we're just working on B right now, right here. All right, we're just kind of moving through each of these. So we're going to go back and we're going to take it at its nameplate, which is 7,000 VA. Again, 7 kVA. We got to convert to VA, 7 times 1,000. Or if you're just used to seeing the K, you know that's 7,000 watts. And watts is synonymous with VA. So we're going to do 7,000 watts. And then we have a wall-mounted oven, which is 6,000. Again, I don't need to explain that again. 6,000 VA. And ignore this right here. This should be right here, should be 14,739. But we did get it right down here. I didn't want to change it for consistency on the webinar that I just did, but just ignore this. This value is from the previous page, which is what this was. So it's 14,739 is what we previously did, plus the 7,000, plus the 6,000, and that's 27,739. Okay, of the cooking loads, we've got 13,000 VA, just in case you wanted to know. So now let's kind of tie all these things together. So the first ones we did was the general lighting, the small appliance, and laundry. We did all that. That's 14,565. Then we did the appliances. We did the water heater. We did the dryer. We did the counter-mounted in cooking unit, and we did the wall-mounted oven. That came up to 27,739. So now we're going to do what it said. We're going to take the values that we have in 220.82b. And now we get to apply some demand factors. And you remember what it said? We take the first 10,000 at 100%. And then we take the remainder at 40%. So let's do this. We added this to this, and we got 42,304. Okay, we just added the general lighting, receptacles, use, the small appliance and laundry. And then over here, we took the fasten in place appliances, wall-mounted oven, counter-mounted cooking unit, the dryer, and we added all of them together and applied it. And that gave us 27,739. So we did it all. And so here we go. 42,304 minus 10. Now, why the minus 10? Remember the first 10,000, 100%? So I'm going to take that 10 and I'm going to sit it over here. We're going to add it back later, but I want to sit it over here. Get it out of the way. So now that leaves me with 32,304. That's the part that I take at 40%. So it's 32,304 times 40%. If you like working it out as decimals, then it's 0.40, however you like to work it out. And the result is 12,921.6. Well, because of that 0.6, and remember that we're dealing in 220.5 says we can use that 0.5 and larger, then we can round up. So in this case, we round up. So that ends up being 12,922 VA. Now we're going to add that 10,000 back, that 100%. And we add it back. So that gives us 22,922. Write that down. Okay, that's what you're going to need later. All right. So as far as part B is concerned, we're done. So if I go back to the NEC, as far as all of this right here, all this right here, we're done. And I only remind you right here that if I have additional permanently connected motors in my equation and they weren't covered under any of these other options in 3, then I have to take them in consideration, and I take that kVA in consideration. For example, a pool pump motor very much is usually going to be a permanently connected motor. Doesn't always have to be, but if it is a permanently connected motor, then I'm going to take that. If it's not covered in these other items up here, and it's not considered an appliance, then and only then will I actually take it and I will add the kVA of that motor into my equation. Okay, I might get the amps or I might get the kVA, whatever. I might have to solve for it if it's a motor, but I count for that. All right, that's what's going to get you in item 4. Okay, just something to think about. Keep it gelling in your mind. All right, now another interesting thing here to talk about in A, as we're just talking about some things, is you notice it says all appliances that are fastened in place, permanently connected, or located to be on a specific circuit. Then you have to account for that value and figure that into your calculation as a load. Again, it's dealing with appliances. So if it qualifies as an appliance, then it's and it's being fed by a specific circuit for that appliance, then I have to take that appliance into consideration. Now, under the standard method, we still had that application. We had to add all these things up. So there's really no different there. The only other thing that I can tell you that's different in here is that we're not applying 25% of the largest motor. We're not doing that for the optional method. Okay? So you don't have to worry about that mess as well. All right? But I just want you to be aware of all these things here. Don't make it complicated. If it's there in your question, apply it. If it's not, don't apply it. All right? Okay. Let's move on now to the presentation. I think I covered that. And again, at the webinar, I forgot to turn it off this page. Once I got there, I kept going, and I apologize. All right, so back to the webinar. So that's 22,922. So write that down. Now, let's take a breath. And now we're going to move on to C. And we're going to deal with the heat and the cooling. Okay? And it's not that complicated. I just want you to know that when you start looking at the NEC and you look at it right here and you see C, that what it says is you want to take the largest of the following 6 selections. Okay, and the load being obviously going to be in kVA, shall be included. So you take the largest option. So you need to know what your system is in order to be able to apply these. Okay, you need to know. All right. I'm just saying. So let's kind of make sure that I'm back at my presentation, and let's look at each one of these. Now, first things first, when I get on an exam or even in real life, when I start getting values for the heat and air conditioning and all that, and I'm giving amps and volts, or if I'm giving horsepower for certain motors, I'm going to have to convert them like I did earlier. If it's a horsepower, I got to go and find out if it's obviously going to be single phase, for this case, single family dwelling. Then I need to go to 430.248 and I need to get with the FLC, or that's the ampacity, and then I bring it back, and then I do that value times the voltage, and that's going to give me my VA. In our example here, we already been given all the amps, and hopefully on your exam you are too, but now you know how to do it. It's not a big deal. So first things first, let's knock these motors and this air conditioning compressor out and get all this out of the way. So 3.2 amperes times 115 volts, okay, is going to give us 368 VA. Okay, didn't kind of put that here, but that's what it comes out to be. The 16.6 amperes times 230 volts, which I have done, is right here. It gives me 3,818 VA. Okay, so that's what the air compressor is. And then, of course, you've got the condensing fan motor, and that is 2 amperes at 150 volts. Again, it's pretty simple. 2 times 115 volts, that's 230 VA. Okay, so of our AC loads, to be honest with you, it's 3818, 230, and 368. Okay, that's what we're considering here. All right, so that's our AC component. All right. Now the heat we're dealing with, again, we don't say in the equation that it's supplemental heat. We don't say that. Okay. Since we don't say it, and we make no reference at all to a heat pump. Remember, for an exam, they're going to tell you it's a heat pump, and then it's going to either be with heat or supplemental heat or whatever. Okay. So we want to take that into consideration. What I told you up front is, based on our system, they are separately controlled heat Okay, and they do work in conjunction with that air handler unit, but it doesn't always mean it might be the case. But in our case, it does, and so it's in incorporation with it. Also, the reason I'm telling you that is if you have some other application where you got the heat and the air conditioning and you have an air handler involved in it, then that air handler system is going to push that air around the building. Then you're going to actually have to incorporate that air handler value with not only the heat, but also the air conditioning. Just keep that in mind. In our equation today, we are going to include that air handler unit with that heat. But for example, it had been 3 baseboard heating strips with separately controlled thermostats, then there is no air handler to be figured in because that has nothing to do with it. That's only associated in our case with the air conditioning unit. Okay, you with me? Hopefully you got that. All right, I just want to lay the lay of the land here so nobody gets confused. On your exam, it might be different, and they're going to tell you whether it's a heat pump or not a heat pump, or whether it's central heating system or whatnot, or it's just a pure AC system. They're going to tell you that. Trust me, no worries. All right, so let's look at each one of these. Now, the first one is 220.82C1, and that is dealing with the air conditioning. And it says 100% of the nameplate rating of the air conditioning and cooling. Okay, well, we have to do the air conditioning value first, and we already did those calculations, and we did this earlier. So you saw how we came up with that. We had to do that. And then once we do that, then we know what the values are, and then we can start out as one of our 6 options, or one of our 6 selections that apply. That's the first one, because we do have air conditioning. It's clear on the screen we have air conditioning. So, of these, you add them together, that's 4,416. That's the total for 220.82C1. You write that down. That's the first one to consider. Write it down. The next one we're looking at is purely dealing with a heat pump. If you have a heat pump, if your question states you have a heat pump, you either have a heat pump with supplemental heat, a supplemental electric heat, or without. Either or. If you have a heat pump that does not have supplemental heat, then you take the AC portion of it at 100%. Okay? And you don't worry about it because there's no supplemental heat. You take the AC portion, or the heat pump value, I should say, the heat pump value at 100% of its nameplate. Okay? And that's what it is here. So again, in ours, we're not going to use it for our calculation, but if it comes into play, then you would use it. Now, in this case, let's say that, just for kicks and giggles, that this was a heat pump, but this is the only part that's a heat pump, and this right here is not supplemental heat to the heat pump. It's something else. Okay? Then, if I did have a heat pump, although, then if I did that, then I'm only going to consider, because if I didn't have the supplemental heat, then I would only use the AC portion of that heat pump, or the heat pump's value that doesn't have supplemental heat at 100% of its nameplate. Okay? All right, but sometimes I do have a heat pump with supplemental heat. So just keeping, trying to give you all the possible scenarios. In our calculation, I've already kind of told you what we're considering. So we're not going to consider C2 as in our option. The next one is C3. And again, in case you lose where we're at, here's what we're talking about. Again, we're talking about all these right here when dealing with the different options. Okay? Just in case you get lost. All right? In case I get lost. So we're back to the presentation. Now, it says 100% of the nameplate rating of the heat pump compressor and 65% of the supplemental electric heating for central electric space heating systems. Okay? So, if I have a heat pump and I supplement it with supplemental electric heating for central electric space heating systems, and I'm supplementing this, then it's saying, okay, well, guess what? If the heat pump's compressor doesn't come on at the same time as the supplemental heat, then I can take what? If it doesn't come on at the same time, then I basically can use the heat, the supplemental heat, at 65%, and I'm done. Now, if there is no statement about the fact that they could possibly come on in the same time, then I'm going to have to take 100% of the heat pump's value in the compressor and 65% of the supplemental electric heat, both, because they both could be there at the same time. But I just want to make it clear that if you get an application where you know that you're not going to have the both of them on at the same time, if that's the case, then I can use the heat at 65%. Okay? And more often than not, in this case, the heat is going to be greater anyway than what the heat pump value is for the heat pump compressor. Okay? So it makes sense. We're not dealing with that one in our occasion. We're just kind of not going to work with that one. We're going to keep it simple. And we're going to talk about these three banks. Although I tell you that it's utilizing the air handler, I'm telling you that. And your question on your exam would have to let you know that. Because on exam, we would say space heaters or whatever. We're going to treat these as separate, individually controlled or separately controlled heating units or heating banks. Okay? That's what we're saying. All right. God, I don't want to make that confusing. Tried to do it so it wasn't confusing. All right, now let's get to C4. Okay, and we have the code says you use 65% of the nameplate ratings of electric space heating if less than 4 separately controlled units. Well, in our case, I told you up front we had 3 banks of 5 kW, so I have separate. Now, I could have easily said that this was supplemental heat and that you considered it supplemental heat, and I could have used the option previously here. And the only difference is if I didn't tell you that one of them doesn't cut on when the other one's on, then I would have had to take the heat pump portion at 100% and the heat part at 65%, and I would have to count for both. Now, if I told you again that they're not both on at the same time, then I can go with the heat and do it at 65%. That's what it says in the code. But in this case, I did this on purpose because I didn't want you to stay in that one about the heat pump. I wanted to say and give you this scenario where I've got electric heat. It's separately controlled. There's 3 banks of 5 kW. Okay. And I'm dealing in this application. And so what? I've got less than 4. In our case, I got 3 right here, 3 of them. Okay. So we have 3 of them at 5 kW. So we've already know what that's going to be. So that's 15,000. But remember I said, because I wanted you to think, our system is designed where it's central heating and it does utilize the heat pump. There are unique systems out there that do that. These aren't baseboard heaters, okay? So in this case right here, we've got the 3.2 amperes for that blower motor right here. And we're doing it, and we already did this times 115 volts. So that's 368 VA. We're going to add that to the heat. And that's going to give us 15,368. Now, in the real world, if you left off the blower motor, probably wouldn't make a difference. And you are going to have applications where you're not going to add the blower motor, like electric baseboard heating, for example. So that's the reason I presented it like I did, because I didn't have a better way to do that, and I didn't want to lock you into heat pump, okay? There's many people that don't utilize the heat pump, but there are heating systems that utilize the heat pump, and you have these air conditioning and the compressor. But once it gets in, we have separate heating unit, but both of them utilize a blower. And I just want you to make sure that you understand when you got to add that blower. And we covered that in the standard method, and it also applies here if that's what's going on. Okay? Just want to make it clear. All right, so, I mean, it's the easiest way I can explain it. Other people might explain it differently. Go for it. So, finally, we looked at that 15,368, and it was much greater than the AC portion of that. Okay, now, even if we had left off the 368, and we said it was a heat pump, whoever out there wants to argue, and I know there's guys out there hitting that thumbs down button all they want, like I care. And even if I did that, it would be 15,000 times 0.65, and that's still 9,750. And it ain't that big a difference. It's still much greater than the heat pump value or the AC value is in that first one we did in C1, which is 4,000 and something. So we're still going to go with this, and this is so far our largest selection, right? So whether I use it as a heat pump with supplemental, which you could argue if you wanted to use this, and some classrooms might. In our case, I painted you the picture where it was not being used as that, just so I could do this and cover both of them. Otherwise, it'd been harder for me to cover it. So Which is the winner here? Obviously, the 9,989 is the winner. And again, that is 65% of the 15,368. Okay. All right, so we got two more that we want to cover, and we'll cover those real quickly, is this option. Now, what if I had an application where I have electric space heating that's 4 or more? What if I had baseboard heaters, or say, and those are electric space heating, and they're separately controlled, again. And if that's the case, then I can apply a 40%. Well, if I apply the 40%, again, if that results in the largest option, then that's what I'm going to do. That's going to be my selection for C in 220.82C. You get with me? You follow me? All right. In this case, it doesn't apply. Either however you wanted to consider these values here, whether a heat pump was supplemental, or you wanted to consider this as separately controlled 3 banks of 5 kW, and we did that at 65 because it's less than 4. However you want to do it, in this case, 5 is not going to apply. Okay, so it wouldn't be the 40%. But I just want you to be aware of it, okay, if you run into that. And then lastly, 6 says, and again, it doesn't apply to our example at all. It says 100% of the nameplate rating, I went back, of an electric thermal storage and other heating systems where the usual load is expected to be continuous at the full nameplate value. So if it's some other type of thermal storage or some other type of heating system that the load itself is going to be considered continuous, means it's going to run 3 hours or more at the full nameplate value, that's kind of the genesis of a continuous load that's running at the full ampacity or the maximum ampacity for 3 hours or more. Well, here we're just kind of saying, look, continuous load, because that nameplate value is going to run continuously, and we know what the definition of continuous is. We get it. We get it. And if that's the case, all it's basically saying is take the nameplate at 100%. Just take it at 100% or whatever that system you're using. All right. In our case, I don't think we're ever going to see one of these maybe in a single family dwelling, but I'm not going to say maybe, never, because you could, and you just need to know how to do it. So we have covered everything here. So let's kind of crunch the numbers and see what we're looking at. So remember, 22,922 was the total for B, and we just did C, and that ended up in 9,989. So we add the two together. Remember, that's what it said to do under 220.82A, add B and C together. So it's 22,922, 9,989. That is 32,911. So now we do our good old math here, and we do VA divided by volts, good old Ohm's law here. Okay, so we're looking here, and it's 32,911, okay, VA, which is kind of our watts, if you will. That's how we get the Watt's law and things like that. And so we divide that by 240, and that's going to be 137.12. Well, you remember what 220.5B told us? Hey, if it's 0.5 and greater, then we round up. If it's below that, you drop it off. Well, this is 0.12. Get rid of it. It's gone. So the total value is 137 amperes. Now, what do we got to do? I need to decide. Now, I know what my load is, my calculated load. Now, don't lose sight of that term, calculated load. Connected load is before we did anything, and that's when we took all those values. We're now at a calculated load. We've done some calcs. We've applied some things here. Okay, we've applied some demands. Now we have to size the breaker. Well, typically we go to 240.6A and we look at the standard table to provide that breaker when we're using a regular inverse time circuit breaker or for a fuse. And that's typically what we're going to use. And obviously in a single family dwelling, that's going to be our choices. So that's why we're picking it here. Now, I want to go to this table and I notice that I don't have anything that's rated 137. So I'm allowed to go to the next standard size. And these are all standard sizes, by the way. And so 150 is the next standard size. So it's 137 amps of calculated load. And I can protect it with a 150 amp rated device because it says that I can go up to the next size. All right. Now, while we're doing that, we now got to start remembering what the question was. On an exam or in real life, if the service or feeder calculation falls between 100 and 400 amperes, And I'm going to look at the smallest possible service conductors that I can utilize and get away with it. And the code allows me to do this. Diversification and whatnot. And again, it confuses people. But the reality is, don't get lost in what we're getting ready to discuss. Just do what the code says, okay? Now, if you want to size all the conductors based on 31015 B16, go for it. Again, I work for a company that manufactures wire. So if you always want to go with bigger wire, I'm all about that. Go with the bigger wire. You're never going to go wrong. Just be careful about the terminals and all that kind of stuff, because you go too big, it might not be the right terminals for the job. So just keep that in mind. They have to be listed and labeled and identified for that application and those sizes. Okay, there's my disclaimer. But when we have it 1 through 400 and it is a single phase 120, 240 or single phase 28 Y120 application, then I am going to be able to utilize 31015 B7. And it's a beautiful thing. So again, real quickly, let's go to the code so I can show you that table, because boy, I'll tell you what, it is, as long as you comply, this thing is going to be a lifesaver for you, okay, in sizing wise. And I just went way too far. All right, so here we go. So this is what you're probably familiar with. And again, it says single phase dwelling services and feeders. Okay, and you see this grayed out stuff means it's a change from previous code cycle. All right, and so it's utilized for the service. It's going to be 120, 240 volt systems, and I'm permitted. It says permitted, shall be permitted to size it in accordance with 31015 B7 1 through 4 for services. Now, feeders are only going to let me use B7 1 through 3. Okay, but when I'm dealing with services, man, I got this all right here. I got 1, 2, 3, 4. I am good to go. So when I want to get the best possible choice on an exam, the best possible size, I'm going to remember that 31015 B7 exists, but I got to meet the parameters. It's got to fall between 100 and 400 amperes, right? It was perfectly fine to be used for single family dwellings, for individual dwelling units. And again, remember, one family dwellings is a dwelling unit, so don't get lost in that. Okay, that I can utilize these applications for this. I can also use this for individual dwelling units of two family and multifamily dwellings. So if I'm calculating the feeders, for example, to those individual dwelling units, then I can do so. If I'm also sizing the service to those individual dwelling units, if that exists, then I can utilize this, okay? Just be careful, okay? That you understand that you're meeting all these parameters. If you don't know how to do this, we have a video that's out called Derating Demystified, and it's got, I don't know how many thousands of watches or views or whatever. Go watch it. You'll learn all this stuff about conductor sizing, whatever. And I assume that you want to watch it because in the 2020 code, all that changes. And we got to do it over again. It does. It changes. So anyway, go watch it. Now, when you're dealing for one family dwellings and those individual dwelling units of a two family and a multifamily dwelling, and all those for you naysayers out there, the reason we call them individual dwelling units right here is because we're talking about more than one dwelling. Okay? That's why we need to identify it as individual. So it's a two family dwelling. You have one individual dwelling unit here, one individual dwelling unit here. They're still dwelling units. They're still single family dwellings if they're separated, by example, by a firewall. I have one over here, one over here. Please don't get lost in that. If you don't believe me, ask every other educator in the country who has books and videos out there. You'll see them say, yes, you can use the optional method for a single family dwelling. All right, don't go there. I don't want you to go there. People don't like their mind. We go, and it's all good. Everybody has an opinion, but it's my students. I don't want to go there because you would be wrong. All right, so in our case, we're looking at a service. So we're here. We're going to be rated 100 through 400 amperes, and our calculation was, remember, it was 150. Okay, so it falls in here. Other thing to remember is, in order to use this table or to use this calculation, that those service conductors have to handle 100% of the load, folks. 100%. What do we mean? Well, I'm going to paint you the picture, because I didn't have a slide for it. So I'm going to paint you the picture. 100% of load. I've got a meter on a single family dwelling. Power comes from the service drop down to the point of attachment, down to the service head, down to the meter, through the meter, to the actual service. Okay? Now, all of that right there is 100% is being supplied by that panel with all those loads. Everything's in it. All the loads are in it. Then I can size those conductors from the point of attachment all the way down through the meter to the service on the line side based on the allowances of 31015B7. No problem. Now, what if I go from that panel that has breakers in it and I go downstream to another panel, a remote distribution panel? I can't use the allowance of 31015B7 for that application now because that downstream, that feeder running to that downstream panel is not handling 100% of the loads. There's some loads in the first panel and there's going to be loads in the second panel. So I've got to use 31015B16, the normal ampacity table. Okay, you with me? All right, now let's do another scenario. What if I come down the pole, or it could come underground too, it doesn't matter, but I like the overheads. It comes down to a meter, and next to the meter is a disconnect. That's your service disconnect. Now, it wants, say I want to put that panel, which is now a remote distribution panel, I don't want it to be on that outside wall. Maybe it's a bedroom. Maybe I want to put it in a room that's inside the house somewhere. No problem. Now, we have a feeder, because it's on the load side of the service disconnection means, or the service equipment. Okay, so you're going to run 4 conductors, you're going to run it downstream. Now, in that application, because I had the disconnect outside, and it simply goes from that one disconnect, main switch, and now it feeds the panel downstream, that panel downstream is still handling 100% of the loads. So yes, that feeder can utilize the allowances of 31015B7. No problem. You get me? You follow me so far? Because that panel and those feeders and everything associated with it are still handling 100% of the load. Okay, now let's get to the no-no. The no-no would be in a scenario where I've got a outside overhead, it's coming down and it's hitting the meter, and then it's hitting another panel. And maybe the reason I hit that panel is because maybe it's a feed through and I've got 4 circuits there. And because of convenience, I've got an AC unit right there, compressor unit outside, okay? Right there. And I'm thinking, God, I'm already here. I'm going to put a 2-pole breakers in here and I'm going to feed these air conditioning units right here. And then I'll continue on to my panel that's inside. Okay. Maybe that's what I'm doing. And so maybe I'm in that panel and maybe I don't have a main breaker out there. Maybe I'm trying to comply with the 6 disconnect rule and I'm only using 2 of the 4 of the spaces, or 2 2-pole spaces. I don't know. But the point is, I'm out there and I'm not handling 100% of the load because some of the load is out there in that panel. And now when I go to feed the panel inside, it's handling some of the load. So it's important that you understand, in order to use 31015B7, whether it's the feeder or the service, that the conductors in question that we're going to apply this minimum of 83% to, it's got to handle 100% of the load so that it takes full advantage of diversity. That's important. So make sure that all that applies, and then you get to apply 31015B7 in your application. All right? So hopefully you got that. All right, back to the actual presentation, and we kind of round this thing out. All right, so we're going to apply that because ours does fall between 100 and 400. Again, it was 150. We calculated it out. And if you looked at the code again to make sure it's clear, you'll see that here is where we get the conductors cannot be less than 83% of the service rating. And the service rating was that 150 amperes that we figured in. Okay? So we've already got that written right here. So 83% of 150 must be at least that size. At least that size. Okay? So to do that, it's pretty simple. 150 multiplied by 83%, or 0.83, is going to give us 124.5. And because it's 0.5, remember what it said in 220.5b is we're going to round up. So it's 125 amperes. We did that. Okay? That's what we're dealing with. But we know that the service breaker or service rating is going to be 150. But yes, we can have a conductor that is going to be based on 125 amperes, and it has to be at least that size. That's 83% of the service rating. Many people freak out on that because the code says, you know what, the conductors has to be sized to handle the load. Well, here I'm allowed to do that in this application. Now, in our case, it just happens to work out. We didn't have any issues when we're doing the optional method. But just don't get lost into it. Everything is okay. Don't get concerned about when it's sizing in this application. All right. Remember what we were at, and we couldn't find when it corresponded, so that's why we ended up going up. And I think if we go back, it was right here. Okay. We had 137 amps that didn't correspond, so we go to there. Here, we are saying that it's perfectly okay, per the code, to have a 125 amp rated conductor and it terminate on a 150 amp device. Perfectly okay. Now, if you're used to doing motors and you're used to doing HV system, this is not going to scare you. For many people, they look at this and go, oh my God, no, you can't do that. There's a violation. Code says you can do it, do it. It's all based on diversity. It's all good, my friends. Don't worry about it. All right, so now we got to have a conductor. Now, we are going to be in the 75 degree C column. Now, people ask me why. That's because we're dealing in over 100 amperes or more. So in 110.14C, you've got the C1 and C2. C1's dealing with 60 amperes or under 100 amperes. It's going to be a 60 degree column in 310.15B16. And then when you're dealing with over 100 amps or more, then you're going to be in the 75 degree C. Okay. Remembering now, we can use the 90 degree value under 310.15B16 for adjustment and correction purposes. The code tells us we can do that. All right. Now, most wire today, THHN, THWN-2, that -2 means it's 90 degree rated insulation. Okay. Wet or dry. If it was just THWN, it would only be 75 because it only has one H, so that means it stays in the 75. So I'd have to do any adjustment and corrections or whatnot from the 75. But the beautiful thing about the -2, whether it's on thermoplastic or thermoset being XHHW, for example, the reason that -2 is important because it tells me that I can use the 90 value ampacity-wise for adjustment and corrections, that I can, and that's important, all right? But we're in the 75 degree column, one, because typically that's what the terminals are going to be rated for. It's 60 or 75, either or. But remember, if you don't understand about terminal limitations, go back and watch my video on derating demystified, and you'll learn all about terminals 110.14. In our case, we told you the terminals are 75 degrees C, plus it is over 100 amperes, so we know that. Okay, so that's where we're falling, and that's why we're in 75 degrees C. Now, under 75 degrees C, I need a conductor that's going to give me at least 125 amperes. All right? So let's go to the code. I'm already over an hour now, so we might as well just do it. If you've zoned out, I apologize because my videos tend to be long. Hopefully you got something out of it. If you're in my Fast Tracks program, then you need to watch the video, so you better keep watching. All right, so 310.15B16, 75 degree column. We're going to come down. I need something that's going to handle 125 amps. Well, 2's not going to work right here. So 1 gauge, good for 130. All right. Can a 130 amp rated conductor handle 125 amps? Absolutely. So that's our copper conductor. Now, what about aluminum? Same 75 degrees C column. We're simply looking for a conductor based on terminal limitations. And remember, I haven't said anything in here about adjustment and corrections, so we're not even putting those into play. But if you did have adjustment and corrections based on the number of current carrying conductors or an ambient temperature, then you have to apply them. And that's when you get to use the 90 degree rating of the ampacity to apply those adjustment and corrections. Okay? Again, not going to go into that here because I didn't bring that up here. Go watch our derating demystified video if you need to understand how to apply those. Because I also talk about 310.15B7 at the end of that video. So you got to watch the whole video to get that tidbit of information. All right. So if it's 2-aught, or excuse me, if I'm looking for something that's going to give me 125 amps in aluminum, then I got to go to the code and I'm going to go to the same 75 degrees C right here. And I'm going to go down and I'm looking for... I need something to give me 125. Well, 1-aught's not going to work. All right, so I need at least a 2-aught. So there you go. 2-aught aluminum. That's what I need. So the difference in the two is a 1 gauge. I can use a 1 gauge for copper, or I can use 2-aught for aluminum, either or. Now that I know the conductor sizes, if I gave you a pop quiz, and you can't see the whole thing because I leave my body's blocking this, but here's what it says. What is the minimum size of the grounding electrode conductor to a water pipe grounding electrode? Okay? And assume it's supplemented, means that there's some other electrode, because you always have to supplement a water pipe electrode. It's assumed that it's supplemented, and it's a metal water pipe, okay? Let's get that out of the way. All right, if it's a plastic water pipe, then that wouldn't be electrode to begin with. So why would you run a grounding electrode conductor to it? Come on, people, think a little bit. All right, so I've supplemented it with, say, 2 ground rods, so that's gone out of the way. But what do I size that grounding electrode conductor to that metal water pipe in this rule? Well, you should know, if you watched any of our videos, that I'm going to base it on the size of the conductors, and it's going to go to 250.66 to do that. So we're going to go to 250.66, so I might as well round it out and explain all these things to you, because I know that you're preparing for an exam. You want to make sure that you know all these things. So I'm going to go down to 250.66 and show you what you do. Now, one thing I will remind you is that you do have what's called A, B, and a C. If you've got ground rings, concrete encased electrodes, or rod, pipe, or plate, then you have these kind of like exceptions, if you will, that are in lieu of the general rule. You can apply these, and they tell you that the conductor doesn't have to be any larger than what they give you here. In our case, water pipe ground, a metal one, is not covered here, so you have to go to the table as it references in the general rule of 250.66. So right here, it tells me to go to the table. So I'm going to go to the table. Now again, this table is based on the size of the largest ungrounded service entrance conductor. In our case, it was a 1 gauge. We're going to use copper. So right here is a 1. So it tells me it has to be a 6. So that is a conductor that goes from the panel down to the grounding electrode. And that is called a grounding electrode conductor. And it has to be at least 6 gauge copper based on this right here, at least to the water pipe. All right. Now, if I wanted to run aluminum to this water pipe, and remember, I can make this connection anywhere within the first 5 foot of entry. So it could be viable that I run aluminum. Yes, aluminum can run as a grounding electrode conductor. Then it would be a 4 gauge if that's what I wanted to do. Code allows for me to do that. Many people don't know that, but you know that now. So, but that's how you size a grounding electrode conductor. All right. All right, so that's the little pop quiz. All right, now, that's pretty much it. We sized all the conductors. Now, if you were sizing a neutral, you're going to now have to go to the standard method. And when you go to the standard method, what are we going to use? Well, we're going to use all of the values that we got beginning, the 3 VA per square foot, we're going to use the small appliance branch circuits. Why wouldn't you? Because they're 120 volt loads. You got to use them. The 2 laundry circuits, we're going to use those. Those neutrals count. We're going to do all the same values of everything that we added up here in green before, as you see right here on the screen. All of these, because these are all 120, so they contribute. The difference is, since I have 4 or more, then the 75% demand factor will apply to these, and that's a benefit. But that's only in the standard method. Go back and watch the standard method video. The clothes dryer, counter-mounted cooking, and the wall-mounted oven, you're going to use the values that you're allowed, but in that case, you're going to have to use 220.55 for the ranges, and you're going to have to use 220.54 for the dryers, and in that case, you're going to take 70% of that value and add that to your neutral calculation. Again, go watch that video. I'm not going to rehash that here, otherwise this thing could be 2 hours long. The next thing we're dealing with is you don't have to add the heat here because that's 240 volt. There's no 120 associated with that. And then you've got the air handler, and then of course you've got the condenser fan motor, and of course both of these are 115 volts, so they too would apply as well. And also don't forget that you're going to have the largest motor that has to be applied as well. That's 25% of the largest motor, okay? That has to be taken into consideration. And of course that's a 25% of the largest motor that utilizes a neutral load. So make sure you get that. So hopefully you got something out of this presentation. Sorry I had to do it twice for those that watched the webinar. It is what it is. I apologize. But we covered it. You got to see it. If you have any questions, please feel free to email me at info, I-N-F-O, and it's masterthenec.com, and I will get your emails. I will answer your emails. You can also, if you're a part of our Fast Tracks program and you're taking this as part of your lessons, then you also have what's called Construct Yard, which is inside of the software, our program software, and that allows you to ask a question to us at any time during your studies if you get confused about something. Okay, it's all covered. So hopefully you got something out of this. Until next time, guys, stay safe. God bless.